Hey everybody, Dr. A here, and in this video we are going to be discussing material properties and specifically the stress-strain diagram. So this is a good video for you to be writing stuff down along the way and kind of pausing and maybe rewinding a little bit as we discuss these different attributes. Remember, the best way to learn this material is by writing it down. Watching and listening is usually not good enough. So let's go ahead and get started. What is the stress-strain diagram? Well, the stress-strain diagram, are also known as the sigma epsilon diagram, is exactly what it sounds like. It is stress, which is sigma, versus strain, epsilon, okay? Now, when we are talking about and dealing with stress-strain diagrams, we have two general types of stress-strain diagrams. One of them is called the conventional stress-strain diagram. And on the conventional stress-strain diagram, we are plotting sigma as calculated as force over initial area versus epsilon, which again is strain, as defined as deformation over original length, okay? So A naught and L naught are original area, specifically cross-section area, and gauge length, or we'll just put length, respectively, of a specimen from either a tension test or compression test. And we'll talk a little bit later about more specifically about a tension test, okay? So again, we have force divided by area versus deformation divided by original length, okay? And so when we plot this, what we end up generating is a graph that looks kind of like this. So our vertical axis is stress, our horizontal axis is strain, and we will generate a graph that has the for most materials has the following kind of shape. You have this linear region, and then you end up with this kind of non-linear region that's, you know, roughly horizontal. Now this is exaggerated. I'm exaggerating this. It's really not this pronounced. And then you transition into this highly non-linear region until you finally have some kind of fracture or complete failure of the test specimen that you are using to generate this diagram, okay? Now, we perform a tension test or a compression test to generate data so we can plot this diagram. But what's great about that is once we've plotted this diagram for a particular material specimen, from that we can extract a lot of the properties of that material that the specimen was made of, okay? So we're first gonna just talk about the diagram itself, and like I said, a little bit later I'll get into some of the details of a tension test, and I'll talk a little bit about a compression test. So let's just talk about this diagram first before we get into all the details of how we generate it, okay? So first, we have this linear region, okay? This is this region right here. This is what we call the linear elastic region, okay? So that extends to about right here, okay? This is the linear elastic region, okay? And then beyond the linear elastic region, in most of this this kind of horizontal piece of the stress-strain diagram right here, this is your yielding region. So this is where the material itself begins to yield or experience permanent deformation, okay? After that, we encounter what's called the strain hardening region, and that's about right here, okay, this region right here, strain hardening. Strain hardening. Now, in this region, your material is able to, it's experiencing permanent deformation. It's being permanently deformed. However, you do have an increase in its stress carrying capacity here. Its allowable stress or stress carrying capacity does increase. But then beyond that, there's a decrease in its stress carrying capacity. And that region is the necking region, which then finally leads to ultimate failure. So this region right here would be necking. And then at this point right here, you have fracture. Okay, you have fracture here. So these are generally the main regions of your stress strain diagram. Now, from this diagram, again, we can pull off some important material properties. One of the most important material properties is the slope of the stress strain diagram, okay? The slope of the stress strain diagram. So the slope of the linear region of the stress strain diagram, I'm sorry. So we're going to call this capital E, and we call this the modulus of elasticity. Okay, also sometimes called Young's modulus. Okay, and this is the slope of the linear portion of the stress strain diagram. Now, if you look at this linear portion here, you can relate stress and strain and Young's modulus by a handy little equation, which we sometimes call Hooke's law, okay? So if you just look at this, it's a linear equation, right? It's a linear equation. So this is the slope. Oops, didn't mean to edit that. This is the slope E. And you notice that this line passes through the origin. So what would the equation of that straight line segment be that we also call Hooke's law? Well, it's just y equals mx, right? So in this case, it's sigma equals E epsilon. Notice again, this has the form y equals mx, okay? So that's a linear equation that has like a y-intercept of 0, okay? And again, if you think of like rearranging this, we can see obviously E is equal to sigma over epsilon in the linear elastic region. Now, one point that people kind of get confused on is sometimes people think that we can just use this equation anytime we're doing anything with a stress strain diagram. That's not true. This equation is only valid in the linear elastic region of the stress strain diagram. And a little more specifically, it's really only valid up to the proportional limit on the stress strain diagram, which is another important value that we get right about here, okay? So we call this sigma PL, and we call that proportional limit because this represents basically the last stress value. So it's sigma PL sigma's a stress value. It's the last stress value that represents the very end of this linear elastic region, and after that you start yielding. So your stress strain diagram starts to become slightly nonlinear and kind of has some curvature to it right past that proportional limit. Okay, so again we call this relationship sigma equals E epsilon is known as Hooke's law. Okay, and again, it's only valid for that first initial linear region of the stress strain diagram on this linear portion right here. Okay, so another really important property that you can get from the stress strain diagram is what's called the yield stress, okay? The yield stress, which we call sometimes sigma y, is an important value that you can obtain from the stress strain diagram. So I'll say is obtained by applying what's called the 0.2% offset method, okay? Now, if you're familiar with this already, basically how it works is you obtain this yield stress by sketching your stress strain diagram. So I'm just gonna resketch it right here, so I'm not working with that cluttered diagram I already drew that's and scrolling back and forth. So I have this linear portion right here, and then it kind of becomes nonlinear, and we start taking off way over here, and we have failure. So in order to determine the yield stress of a material, what we do is we go to the epsilon axis and we go to a 0.2% strain value. Now, remember 0.2% strain, 0.2% strain is the same thing as 0.002 length over length on the epsilon axis. So if you have an epsilon axis of, say inches over inches, or maybe millimeters over millimeters, remember strain has units of length over length, then you would go to 0.002 on here, okay? So 0.002, and you start here, and then what you do is you sketch a straight line segment that is parallel to this linear segment of your stress strain diagram, okay? So we're going to sketch a parallel line, a line that is parallel to our linear elastic portion, and we sketch that up until it intersects the stress strain diagram, okay? And then what you do is you move over, and where your horizontal projection intersects this stress axis, you have sigma y, the yield stress or the yield strength, okay? So so that's another important material property that we use in analysis and design of structural and mechanical systems, okay? So that's the yield stress. There are also other important properties that you can obtain from the stress strain diagram. One of them is called the modulus of resilience, okay? So again, I'm going to resketch another stress strain diagram just so I'm not, drawing too much on top of each other. So let's just kind of resketch this, okay? Modulus of resilience, what is that? So the modulus of resilience, U sub r, it's typically labeled U sub r, modulus of resilience is given by the area beneath the stress strain diagram up to the proportional limit, okay? So this is equal to area beneath the linear elastic portion of the stress strain diagram up to sigma PL, the proportional limit, okay? Right there is sigma PL, okay? And then, of course, this is epsilon PL because that's the strain value that corresponds with the stress value at the proportional limit. So that's the modulus of resilience, okay? So this is kind of like a modulus of resilience is a type of energy, and it's kind of like represents the ability for a material to kind of recover and rebound in terms of an energy, okay, like a stored energy. All right. So this is very commonly a common property that more mechanical engineers use when they are designing mechanical systems that are used to absorb vibrations or shock. Okay, so that's modulus of resilience. Another important property, and this is going to be the last one we talk about in this video. By the way, this is not all the properties we get from the stress strain diagram. I'm just kind of hitting the highlights. But another important property that we can obtain from a stress strain diagram is what's called the modulus of toughness. So again, I'm going to resketch this stress strain diagram, okay? And we're going to talk about this modulus of toughness. Well, what's that? The modulus of toughness is the area under the entire stress strain diagram, okay? So we sometimes call this U sub t, and again, it's called the modulus of toughness, and this is equal to the area under the entire stress strain diagram. Now, you may be looking at this and you may be wondering, wow, this the shape of this is very difficult to capture the area beneath. Yeah, that's true. So you would typically use some kind of numerical method or numerical geometry to help you capture all of this area beneath this entire stress strain diagram. So, you know, you could use some software to help you do that, Excel, maybe MATLAB. One way you can do it is you could take your diagram and split it up into simple shapes. Maybe, you know, a bunch of trapezoids and a bunch of rectangles, and then approximate the area under this highly nonlinear entire stress strain diagram. Again, the modulus of toughness, if you're ever going to actually calculate it from real data on a stress strain diagram, you are probably going to use some kind of numerical method, you know, either numerical geometry, or, you know, you could put some data in Excel and break it up into several little trend lines and display the equation of all these little trend lines on your Excel spreadsheet, and then integrate, right? You take find the integral of all those trend lines, and that'll grab all the area underneath here. Or you could use, you know, a numerical method from calculus, like, you know, trapezoid method, midpoint rule, something like that, Simpson's rule maybe. A few different good numerical ways to get that modulus of toughness from actual data, okay? Now, if you remember towards the beginning of this video, one of the things I said was there are two types of stress strain diagrams, two common types. One of them is the conventional stress strain diagram, and we just talked about that. Really, it's generated from running a tension test or a compression test and calculating stresses and strains using original area and original length. And then from that, you generate this diagram, and you can get all these cool properties, okay, that we all went through already. The other type of stress strain diagram is what we call a true stress strain diagram. Okay, so let's talk just a little bit about that. All right, a true stress strain diagram. Okay, now in a true stress strain diagram, you can still get pretty much all of these same kinds of properties. The biggest difference is stress is computed based on an area, specifically cross-section area. So we'll say a cross-section area value, and epsilon, so strain, is computed based on a length value at a particular point in time while the tension, I'll put in parentheses, or compression test is running. Okay, so instead of calculating a stress based on an original cross-section area the whole time a test is running, and a strain based on the original length while from the beginning of the test, you are calculating stress and strain based on a cross-section area and a length, a gauge length, in real time while the test is being run throughout the duration of the test. And because of that, you'll get a similar shape stress strain diagram, but it won't be the same exact shape. You know, then it depends on the material, but it won't be exactly the same shape. You can still calculate all these material properties we just talked about with the conventional stress strain diagram, but they will be slightly different if you are using a true stress strain diagram instead of a conventional stress strain diagram. So that's it in a nutshell. In another video, I'm going to talk a little bit more specifically about the tension test. So you can check that out in another video. That one will be much shorter than this video, I promise. And then we can look at some numerical examples of executing these properties and determining these properties in other subsequent videos. So thanks for watching. Hit like and subscribe.